About reinforcement learning. So this is a very different type of topic compared to what we've been talking about so far. And in particular, it's different in the sense that the decisions we'll make will be about what actions to take. So for example, this is useful for robot navigation, right? The robot has to take certain actions to go in certain directions, right? So in reinforcement learning, the decisions we make will be about what actions to take. And this then will influence what examples we see next, what state of the world we are in. So our decision will influence what we get to see next, which is a bit different from, say, supervised classification of things that we've been talking about so far. Okay, and also, right, so our decisions are going to influence the next example we see, and also our goal will not necessarily be to just do some predictions, like for example, whether there is a door in front of us or not, but we would also want to be able to decide what to do, what action to take. Again, in which direction should the robot go? Yeah. So that's kind of interesting, different type of machine learning problem. And in order to talk about such problems, we're going to use something called a model called Markov decision processes that I'll define in a bit. Okay, so right, and actually a very cool aspect of this topic, actually is that we have delayed feedback. And in particular, the main impact of our action is not going to come right away, but instead it would come much later. Okay, just as a toy example, so imagine that we have a robot moving in this grid over here. So we have 6-cell grid, right? So imagine that we have a robot moving in that 6-cell grid. Now, if the robot is, say, in this cell here on the upper, I guess, upper left, yes, then no matter what action our robot takes, either if the robot decides to go down or to go to the left, his reward will be 0. No, he has only 2 actions he can take in that position, right? If I'm in this position over here, this one here, I can only go down or I can go left, right? And in both cases, I get reward of 0. However, if I go to the, sorry, I said left, it should have been right. Yeah, I can either go, right? I can either go down or to the right, right? But if I decide to go to the right, that's good because I get closer to my goals. Because let's assume that the goal is to get into this state G over here. That's the goal state, right? And so, and as you see, if once I enter that state, I get a reward of 100, right? So basically, again, this is a simple example showing that in reinforcement learning, the main impact of our action is not going to be right away, but it can be in the future, right? And so, like in this example here, if the robot is here, he can, no matter what action he decides to do now, he gets a reward of 0, but one of them gets him closer to its goal, so we're going to get a big reward. Okay? Or as another example, if reinforcement learning is used for helicopter flying, and so in helicopter flying, a bad move will not necessarily crash the helicopter right away, but it can lead to a sequence of really bad moves that will result in a crash. Okay, cool. So that's reinforcement learning, and just because I have this picture over here, so one of the main ideas of reinforcement learning somehow, and you'll see in the lecture, is like how do we actually act, or how do we decide what to do next? What policy should we take? So one of the main ideas here is to somehow define something called a value function, to somehow be able to come up with some, for each state, to come up with some number, which would be kind of the optimal discounted reward if we behave optimally from that state from the moment on, right? And then somehow it turns out that by then being greedy with respect to these values, we're going to be able to act optimally. Okay, this will become much more concrete in a bit, but just to give you some high-level idea about the type of algorithms we'll be talking about. Great, and just in terms of applications, so, I mean, some obvious ones are like robot navigation. That's an obvious application, but there are other, another application that was a really cool one that made reinforcement learning really popular. It's playing games. Okay, and in particular, Jerry Tesauro from IBM, he's my friend, so in '95, he had a nice application of reinforcement learning for playing backgammon. Okay, and so in this case, so here basically the states or the learning tasks, right? So we have a state of the board, right? This one here, and then the learning task is to decide which state moves to next, right? And but clearly here, so this is we get no immediate reward for doing so, But the real reward comes at the end of the game where we win or lose. Right? So it's again delayed feedback. Okay? And it turns out that Jerry Tesauro used reinforcement learning together with neural network to come up with a game playing technique for this game. And it turned out that it was competitive with the human players, which is kind of cool. Okay, so it shows the power of these techniques. Okay, cool. So, right, so that's the outline. So we're going to talk about a little bit about define the problem formally. We're going to talk about MDPs, a model that will allow us to model these problems formally, and then we'll talk about learning procedures within MDPs. Okay? Okay, so here is formalism here. So the formalism is as follows. So we have an agent that lives in some environment, and the agent is at any moment in time in some state, right? So it could be, for example, a robot, and the robot maybe has some goal, maybe to, I don't know, to open a door, to deliver some pizza, and so on, right? And then so the state the robot could be in is, right, a state in that case would be where the robot is, what direction is it pointing to, and so on. That could be our state. Or in the backgammon playing game, then the state would be just which state of the board are we in, right? Right, so basically, again, the setup is we have an agent, and the agent is in some state of the world, right? And in any given state, the agent could take an action. Right? For example, if I'm in state S0, I don't have my pointer with me either, but good. So if I'm in the state S0, right, then the agent could take the action A0, for example, some action A0, right? And then when it takes the action, the robot gets to see some reward. Maybe gets to see the reward R0, right? And then it enters another state, say state S1, then decides to do another action, say some, abstractly speaking, some action A1, gets reward R1, then enters another state, potentially in a probabilistic manner, right? Because maybe they want to take an action, the next state could be a probabilistic function of the current state and the current action, right? And then so again, our robot is maybe also in state S1, did an action A1, got reward R1, enter another state S2, and so on, right? So just the agent operates within the world. Okay, and then the goal, okay, so that's the setup. And what is our goal when we do reinforcement learning? The goal is to somehow get the robot to choose action to maximize the long-term discounted reward. Okay, there are multiple goals, but for the lecture today, we're going to focus on one specific one, and that's to maximize, we want the robot wants to choose actions so that he maximizes his long-term discounted reward. Okay, and what do I mean by this? I have a discount parameter gamma. You can think about gamma as being 0.9. So that would be my example throughout the lecture. Okay? So let's think about gamma as being 0.9. And right, what the robot wants is to maximize the long-term discounted reward. And what do you mean by this? Like, so what is the long-term discounted reward? So if the sequence of actions what we do is this one over here that I was just describing, right? So in state S0, you do action X0, get reward R0, and so on. State S1, you enter state S1, do action A1, get reward R1, and so on, right? If this R is the sequence of rewards we observe or we get, then the long-term discounted reward discounted by discount factor gamma will be this expression over here, where the reward we get immediately in the very first moment is R0, then the reward at time 1 is discounted by gamma, the reward at time 2 is discounted by gamma squared, and so on, right? So in general, the reward we discount the reward we get at time t by gamma to the t, okay? And why do I say discount? Because recall the reward is, gamma is the number between 0 and 1, right? So as the time goes on, I put less and less weight on the reward I get at time t as t becomes larger and larger. So one way to think about this objective is that actually we do want to get a lot of reward, right? But we care more about the reward we get immediately, right? That's what long-term discounted reward captures. Okay? So that's the problem setup. So, I mean, that's basically this slide pretty much almost defines the problem, okay? So we have an agent, the agent, there is, okay, actually let me make it even more formal. I think this is what I'm gonna do on the next slide. Good, so just to be totally clear in this model we have, yes?
I'm not very clear on the discount
Yeah, it's an input to the algorithm. It's a parameter. Okay, good, perfect. Excellent question. I always like questions. So basically, what we do here is essentially, so we sum up the rewards we get throughout our lifetime, except so if we do a certain state, if I say in state S2 and we do action A2, then the immediate reward will be R2. But then if it was it was the second time step since we started operating in the world, I'm going to discount that by gamma squared. So in other words, I start in the initial state as 0, and I go for a sequence of states. I get a sequence of rewards. Say at time t I'm in state st, I do action at, I get reward rt. When the reward, there is an immediate reward at time rt that I would get, but then I discount that by gamma to the t. Exactly. By gamma 2 is the number of steps it takes us to write. So, exactly. The reward you get, right? The immediate reward, if you start in state as 0 and that state has a certain, that action has a certain reward, if you take it immediately, you're gonna get reward R0, right? But then for the next one, so your next move would be you're now in state S1, and you're gonna do an action A1 that will have immediate reward R1, but because this is our second as a second move, we're going to discount it by gamma, and so on.
So now we need to find the sequence of states, S1, S2, which
maximizes this, right? Okay, and again, what's the interpretation here? The interpretation you just want, it's like this is long-term discounted reward, and as I said here, I even wrote it on the slide, means our agent wants a lot of reward, but wants it sooner rather than later. I guess just to go back to, for example, to go back to here, right? So to this example that I had here, right? Why discounted reward? Because really, my goal is to really get here in this state G, but I want to do it as soon as possible. So, I mean, if I enter this state G later on, that's less of a desirable policy. I only get reward if I enter the state G. This is the only time when I get 100 as a reward. If for any other move, I'm going to get reward 0. Right? And so my goal, I really want to enter that goal state much faster than later. And so that discounted reward nicely captures this. Yeah?
The picture at the bottom, so the goal reward is 0, but why is it 0?
Yeah, so we'll talk about this picture, we're going to talk about it later. Right now, I didn't even define what it is. I mean, here in particular, it will be 0 just because if you once you state in the goal state, you just loop inside and you get no reward. You are just happy. You're satisfied. There is no need for you to act. But these numbers will become clear later. Cool. So I guess this example helped. Okay, so your question was good. Why that quantity? It's not the only objective that people try to optimize, but it's really the most natural one. Okay, cool. Right, so to specify the problem entirely, so we have some set of states S, right? And for the robot, this was the exact example of a state where the robot was. So for example, I have a simple 6-cell grid, right? I mean, that could be the space of states in that example, right? So here in the example here, the state space would be this possible 6 states, right? So you have a set of states, and we have a set of actions. So for example, in this example, it would be move up, move down, move to the left, move to the right, and so on. So 4 actions possible, right? So we have a set of states, we have a set of possible actions, and at each time, the agent observes the state it is in, and it then chooses a certain action, right, as we mentioned. And then it receives a certain reward, immediate reward, and it changes a state, right, to a new state st plus 1. Okay. Now, in principle, the new state we observe could depend on the entire history, right? The new state we get in could depend, I mean, on everything, on anything we've done or we've could depend on all the actions we've done and all the states we've been so far, but that's hard to think about. It's very complicated and convoluted analytically, maybe even unrealistic. And so a very realistic model to think about these problems is to operate under the Markovian assumption, which means the next state I get in might be a probabilistic function of what we've seen so far and what we've done so far, but it only depends on the most recent history. Right? So in other words, the probability that I land in state st plus 1, given an entire history, the probability that I land in a state st plus 1 given an entire history of states and actions we've been doing and observing, it only depends, so this probability only depends on the probability that we land in state st plus 1, given that in the previous time step I was in the state st and I did action at. Yeah, that's called the Markovian assumption. Okay, and so we make this a Markovian assumption about the probabilistic transition function that tells me, given a certain state st and action at, where do I land next? Okay, and we're going to also make the same Markovian assumption for the reward function, because the reward could also be probabilistic in principle. Right. Okay, and just I guess I have here just a comment about this, about the Markovian assumption, right? So basically, just to think about it, what that means. So if we tell the robot to move forward 1 meter, maybe our robot will move forward 1.5 meters by mistake, say. So it could be a probabilistic function, but basically that should only depend on where the robot was in the previous time step, not what the robot has done until then. Right? This is kind of the one way to think about this Markovian assumption. Okay, so this is basically the model that we're going to consider. So the model is the so-called Markov decision process model, which is, now you understand why it's called the Markov decision process, because we make this Markovian assumption about the probabilistic transition function and about our rewards, right? And so this is the setup, and then as I mentioned already, the goal for us is to basically learn a policy, so technically speaking that will be a policy that will map states to actions. So in other words, this policy will tell us what to do at any given time step. Okay, so I'm going to map a state, right, if I'm to an action. Okay, and then our goal is to learn a policy that maximizes the expected discounting long-term reward, which is exactly the quantity that we're talking about, right? This is what I was asking about, right? So the goal is to basically, the goal of the agent is to learn a policy to maximize the expected discount long-term reward, or the discount factor gamma given as input to the algorithm. And ideally want to be able to do so no matter what is the starting state as 0. Okay, it turns out that for his MDP's models, so when I say Markov decision processes, we abbreviate it as MDP. Right, so for this MDP's model, it turns out that there is a unique policy that is the optimal policy according to this objective, no matter where we start. Okay, and our goal is to find this policy. Yes?
I'm sorry, I think the boundary on gamma has changed from the previous slide. It was 0 less than equal to gamma less than 1, and here it says 0 less than gamma less than 1.
Oh, really? This changed? So these are Tom Mitchell slides, as you can guys see. So it's Tom's typo. So it's like he gets credit for all the typos. It's the first time when I use somebody's slides, so it appears to be more dangerous. I'm just kidding. It doesn't matter. So think about gamma strictly smaller than 1. And we don't want to think about gamma really being 0. These are the non-interesting cases. Right? So is gamma, like if gamma equals 1, it's like when, it's like you put the same, you don't discount anything. If gamma equals 0, just means I only care about the immediate reward, that's a trivial problem. Right? So those boundary cases are not interesting. Okay, so let's think about gamma between 0 and 1. It's so convenient to actually give credit to the people that came up with the slides. Cool, but definitely ask questions, that's good. Okay, great. So that's the goal. And again, basically just to summarize, so in this MDP type of formulation, so we have an agent that acts in a certain environment, does action in this environment, like our robot moves around, observes results, and then gets rewards. And then our goal is to somehow learn a control policy, so learn a policy that maximizes the expected discount reward no matter where we start. Okay, so that's the problem. And right. In general, these rewards can be probabilistic, right? And as we already discussed, here is a simple example. So we have a robot that moves in this six-cell grid world. And here, in this my picture, this would be my example for the lecture. So in this example, the rewards are deterministic. And as you can see, the robot gets a reward of 0 no matter what. So basically, unless the robot enters the goal state and can enter the goal state only from two sides, can enter the goal state from the left and from the bottom, right? No matter where the no matter where the robot is entering the goal. So except for when the robot enters the goal state, the robot gets a reward of 0, and when it enters the goal state, gets a reward of 100. Okay, and you can think, for example, on the boundary cases, right? So, for example, if the guy is here and he's trying to go down, hits a wall, then you can think about staying in the same place and getting a reward of 0, right? Because I still want to think about I have 4 actions, move up, to the left, to the right, and down. And just in the boundary case, you can think that I get a reward of 0 and just stay here. Right? If I hit a wall, I just stay where I am. Okay, so the rewards here are deterministic, and we have 4 actions. Okay, so that's the immediate reward. So here I'm just describing the immediate reward. But recall, in these problems, our goal is to really find the policy which maps states to action, and we want to maximize our expected long-time discounted reward, discounted by gamma. Okay, cool. Right, so that's a cool question. I mean, yes?
So the expectation is over a probability distribution generated by your action policy?
So the policy, let's assume that the policy is deterministic. So given a state, in a state I take an action. But what's probabilistic here, we are saying if we go back, when I take an action, so this is probabilistic. Okay, so let's assume that kind of the policy is a deterministic policy. I'm thinking for simplicity about deterministic policy. If I'm in a state, the robot knows exactly what action he wants to take. But when he takes that action, it might be that the transition is not deterministic. So if I'm in a certain state, right, this is exactly this equation. If I'm in a certain state, say, ST, and if I take a certain action AT, the new state that I get into could be probabilistic. So this is where the randomization comes in. And as I said, in general, this could depend on the entire history, right? This probability could in principle depend on the entire history, but to make our life simple, we're going to assume a Markovian world where basically, given a current Markovian world, this transition probability to the new state depends only on the very last thing we've done and seen. Depends only on ST and AT. So the action AT I did in time T and the state ST I was in. Right, but the policy that we'll think about are deterministic mappings. Yes?
Can you go like 2 slides
Forward? Yeah?
and this?
Yeah.
In this case, the bottom left cell should be providing like some benefit if you are in the boxes, closer to the final output. Like the bottom left should have like 0 reward, but if you move out to these 2 boxes.
This is the definition. This is the definition of the environment. So I really want you to encourage you to write. I mean, so that comes implicitly through the objective function that you are saying. Of course, if you are right, so you are saying if I'm closer to the goal, I should somehow
increase the reward. Like it's not a deterministic 100 points, but it should be like you got 10 points if you reach to these blocks, and then it forces you faster towards the goal.
Yeah, but that will be, okay, so if you go back, that will come once you define the value function. So if this is a word, so all I'm telling you, all the robot knows here is you only get reward if you get into the goal state. That's what the game is. If you open the door, this is, you have declared success. Otherwise, you have no success. And then it's the goal of the robot to somehow put values. It's the job of the robot to then put values on these cells so that he can capture what you said. But if you are here, it's better than, sorry, to capture what you said. If you are here, it's better than if you are here, it will be better for you to move to the right than to go down. It's the goal of the robot to somehow design an algorithm that realizes that. Yeah, but the world is what it is. So the world is, only if you go to the goal state, you're going to get reward because you open the door, you're successful in your task, otherwise not. So no matter where you are, you're only going to, you don't do necessarily something useful for me immediately, but that exactly will be the main trick in reinforcement learning, to associate values on the states that will capture exactly what you are saying. Like, for example, right, you want to say that this state, for example, here, this state here should have a better value than this state here. And that's exactly how the reinforcement algorithms are going to operate. Yes?
Can you summarize what the inputs that you're giving? Are all the rewards provided by us, or we can be manipulated?
This is the input. This is exactly the input here. We know as input a state of action, an action space. Sorry, we know a state space. We know all the states the robot could be in, for example. We know an action space, what actions the robot can do wherever the robot is. And right, so that's the input. And then we also know this probability transition function, which tells us if I'm in a certain state ST and I perform a certain action AT, what's the probability I reach a new state, right? So this might not be deterministic. The transition might not be deterministic, but it's a probabilistic transition. And there are two cases. One of them is the very first case we'll talk about. We assume that we know that probability distribution, and the second case we're not gonna know it. So we're gonna relax that. But in the general case, you know the action space, you know the state space. In the easy case, we're going to know this probability transition function.
But we don't know the rewards. Is that it?
Yeah, there will be two cases. When we know the rewards and we don't know the rewards again. It's the same as with the probability transition function. Initially, we're going to start by saying, let's assume that we know them. What should be my control policy, or my optimal control policy? And then we're going to say, let's assume that we don't know them. What can I do? Yeah? But in both cases, my goal is to then learn an optimal policy, according to this notion of optimality. Okay, cool. So that's our goal, right? And right, we want to learn a control policy that is optimal no matter what is the starting state. And as I mentioned, the cool fact is that MDP such a policy exists. And but the problem is non-trivial because our goal is to learn a policy that maps states to actions. But what we observe is not of that form, right? You know, typically in supervised classification, for example, you want to learn to predict, given an email, for example, you want to know it's spam or not spam, right? And you get examples of that form. You get labeled examples of that form, right? But here, we want to learn a policy, but we don't get policies as examples, right? Somehow. Instead, what we get, we get examples of this form. If I'm in a certain state, and I perform a certain action, so given a state-action pair, what I get to observe is the reward. That's a training signal that I have, right? So that's why the problem is a little bit non-trivial, okay? And it's different from what we've seen. But luckily, it turns out that in the MDP world, we'll still be able to say something interesting. Okay, and the cool question, actually, this hints towards what you are saying, Karen was saying. Like, how are we going to solve this? I mean, as I said, the problem is tricky because we want to learn a policy, but we don't really get as our input as the training examples. We only get examples of this from given a state action pair, or whether it's the reward I observe, right? And that's what we observe as input, and we want to learn a policy, right? And so the key point here is to somehow, as actually Karen was hinting toward, is to somehow be able to define something called the value function for each state. So what is the value function for each state is just, okay, but even, okay, so first of all, okay, I'll define the value function in a second, but first of all, let me just mentioned that once I fix a policy, okay, so what I'm going to do, I'm going to first fix a policy, and then once I fix a policy, and if I start in a certain state S, I can talk about what is the expected discounted reward that I get if I start in state S and I follow that policy. Well-defined notion, right? I start in a certain, I have a policy, pi, it's fixed, that tells me what it maps a state to an action, right? And if I follow that policy from there on, I can define the notion of expected discounted reward if I start in state S and follow the policy pi. Okay, cool. And the goal is to find the optimal policy. Okay, and what the optimal policy is defined as no matter where we start, no matter the state that I start in, I want a policy whose value function is the maximum out of all policies simultaneously for all states. Okay, and it's non-trivial I mean, if it weren't in the Markovian world, then this optimal policy might not exist, right? Because here I'm requiring that the policy is optimal no matter what state I start in. It's optimal for that state. But it turns out that if we, under the MDP world assumption, then this would be optimal. There is a unique optimal policy for all states. Okay? And, right. And we're going to denote, so this policy, let's call it pi star. And given a state S, I'm going to denote by V pi star of S, so the value that I get on state S by following optimal policy pi star, I'm going to denote it by V star of S, right? And I guess the claim is that if we do know V star of S and the transition probability, then we can compute pi star of S. So if somebody, so it's easy to show it. It's simple to see that somehow if I know the probability, the transition probability, and if I know V star of S, then I can immediately compute what is the optimal policy. Cool. Okay, so actually let's just instantiate this concept a little bit. So let's go to our toy example, which is a simple, cute example. Okay, so we have, yeah?
A small question about pi, the policy.
Yeah?
Can we make it a little more concrete? Like, is it a permutation of
Excellent. So I have an example. Awesome. You're asking the right question. So here is the policy. Policy is just deterministic, and here actually this slide even shows the policy. So for our simple example, so we have 6 actions, right? So we have 6 states we can be in. We have in each state 4 possible actions, right? And then here's the policy. So a policy could say it's the green circled, so the green circled arrows will tell us a policy. So for example, this policy says if I'm this state here in bottom left, I should go to the right, because this is what my policy tells me to do, right? Or if I am here in this state in the bottom left, I should go up, because I follow the green circled arrow, right? It's here deterministic, and I'm only going to think about deterministic policies, right? Actually, this is also related to your question. You're also asking, right, Rakesh, right? So Rakesh also asked. So the transition probability from to new states is probabilistic, potentially probabilistic, and so is the reward. But I'm only going to think about deterministic policies. And the cool fact is that if you have an MDP, an optimal deterministic policy exists. So I don't have to randomize. And it's simpler to think about, makes the life of the robot easier. The expectation comes from the transition probability, right? Because if we, again, as I mentioned, so the expectation comes from the reward. Actually, it comes from 2 places. It could come from 2 places. From the reward. So this is the slide definition. Can come from the reward. The reward could be probabilistic, but also the transition probability could be probabilistic. So what I said is, if I'm in a certain state ST and I do a certain action AT, okay, one simple case is I'm just going to go into one state ST plus 1, which is what happens in our simple example, by the way. In our simple example, it's just everything is deterministic. But as I said, in principle, this could be probabilistic. If I'm a certain state ST and I do a certain action AT, there might be a small chance I go into one state, another small chance I get into another state, and maybe a bigger chance I go into a third state. Right? So the rewards, exactly, yeah. So in general, the randomness comes from the transition probability and from the reward function, but the policy is deterministic, right? So actually, I think I see your question. Actually, if I go to this example, there should be no expectation here, because not everything here is deterministic. In this simple example, yes.
So the action and the state
let's assume they are finite. Now, of course, you can complicate the problem, and you can imagine that you have states are defined via features, and then maybe it can be infinite. And I'm sure people have looked at this, right? So, for example, Travis here, who is my student, he's an RTN, the master's RTN is a PhD student. He has a master on the topic. And in your master, did you consider finite state space, or were like?
Yeah, no. So I worked with infinite state space.
Infinite state space, right? So the state space can be infinite, but then you have to describe them as natural machine learning by using features. But for today, let's assume it's finite. To learn the simple concepts through assuming it's finite. So right, so if you are very curious about this topic, talk to Travis. He's an expert. Actually, he worked with the world experts on the topic, like Rich Sutton. So actually, if you go back, when I defined, actually there is a very nice book by Rich, right, on MDPs. This was Travis' PhD advisor. Right, so this book here, right, it's a classic one. How do you pronounce his name correctly?
Rich Sutton, and then it's Andy Bartow.
Andy Bartow and?
Rich Sutton.
Rich?
Yeah, Richard Sutton.
Okay, good. Cool, so you can read about this in this book, yeah? Okay, for today, because we only have one lecture, so we're going to focus on finite state spaces. Okay, cool. So I was going through the example, right? Because Sweat asked. Okay, right. So in this example, I should have no randomness. But what is a policy to instantiate? It's, for example, here a policy is the green circled, right? So for example, this says if I'm this middle up state, I should go down because the green circled arrow tells me to do. If I'm here, I should go to the right. If I'm here, I should go up, right? So this is an example of a policy. Maps states to actions. And here I also have the immediate rewards, and this, I said it many times already, I only get reward if I enter the goal state. Yeah, so that's an example. And let's actually compute on this example the value of this policy, depending on where I start, right? So, for example, if I start here, right, right, what is the value of my state? If I start here and I follow the policy, go up and I get 100, right? Because then even once I get there, I'll stay inside the goal state forever, and I get 0 for staying there forever, so I get 100, right? Because I get 100 times 1 plus gamma times 0 forever. Yeah, good. And so that's why it's what it is. Now, what if I'm in this state and then I follow my policy? What if I'm here and I follow my policy? What do I get? Right? If I'm here in this state and I follow my policy, what is my policy telling me to do? What is the green circled arrow telling me to do? Go right. So then if I go right, I get a reward of 0, right? But then 0.9 times 100, right? Because then I'm optimal from the moment on, right? Now, how about, so that's why it's 90. Okay, how about if I start here? If I start in the middle up, somebody else wants to volunteer? The number is there. All you have to do is to explain to me why is that number. It's 81.
Gamma square. Go down and go right. It's gamma square times 100.
It's gamma squared times 100, right? Exactly. And gamma squared will be 0.81. Perfect, right? So that's basically, this is an example of what would be right if I follow this policy, right? Because these are the values I get from each beginning state. Right? This is not the optimal policy though for this example, because the optimal policy for this example, I wouldn't want to go down and then right here, right? Because I could get a much better reward if I go immediately to the right here, for example, right? So the optimal policy actually, it's now this one, the green circled one, but here is an example of an optimal policy, which is basically just follow the shortest path to the goal, right? So no matter where you are, right, no matter where I am, I want my goal, I only get reward if I enter the goal state, and so obviously what I should be doing, because the reward is discounted, right? It's immediate reward 0, and the long-term reward is discounted, I should just follow the shortest path. I should go as quickly as I can to the goal state, right? And actually this example also helps us at least understand on this example why an optimal policy exists. Why there is an optimal policy that is optimal for no matter where it is that I'm starting from, because here kind of the optimal policy is to do the shortest path. And in general, if you think about subpaths of shortest paths are shortest paths, right? If the shortest path from A to C goes through B, then the path from B to C should also be a shortest path, right? If I have a path from A to C that is overall a shortest path, and it goes through B, it better be the case that the segment from B to C is also a shortest path, right? And this immediately explains, for example, why in this example, and more generally conceptually, why there is a unique optimal policy. Yes?
Isn't this NP hard then?
No, finding a shortest path is not NP hard. Actually, so that would be our next. It turns out that you can find shortest paths by using dynamic programming algorithms. So shortest paths is one of the cool problems in algorithms where we do have polynomial time algorithms. Yes? This is, that's great. This will be like, in this case, will be single, in this specific example, this will be like a single sync shortest path. I would want to find a shortest path to G, and turns out that we have algorithms for it. And actually, that will generalize, actually, the algorithm that we're going to talk about, because the next topic will be, assume that I know the transition probabilities, and assume that I know the reward functions, and how can I compute an optimal policy? Assume that I know everything. How can I compute an optimal policy? Turns out it's kind of like a shortest path problem, and I'm going to do dynamic programming. Okay, most problems are hard. Most combinatorial problems are hard, but shortest path problems are not hard. There are a variety of algorithms, and many of them dynamic programming based. Yeah, more questions? Yeah, that will be the next topic. So we'll talk about it. The transitions, they could be probabilistic too. We'll talk about it. There will be extensions of it. So there will be algorithms that say if I visit every state action infinitely often, then somehow I can still learn. Okay, that will be the second part of my lecture today. Yeah, actually this topic is also cool because it has connections to cool algorithmic technique like dynamic programming. No? So actually we're going to use dynamic programming to solve the question when everything is known. Excellent. Cool. So right. So now our goal is to basically right. So now to go back to you guys all have the questions. How do I actually operate in this environment? Okay. How do I do something interesting? Right. So let's assume that we know the action space, the state space. Let's assume everything is finite. We can list them. Right. So we're going to have polynomial time algorithm that is polynomial in the size of the action space and the state space. Okay. And let's assume that everything is known. That for now, for simplicity, we'll assume that we know everything. We know the transition probabilities, we know the reward functions. Okay, and how we're going to operate? Well, we're going to introduce exactly what Karen was saying, something called a value function that will be defined as follows. So, for example, right, so what is a value function? So the value function is exactly we already defined the optimal policy, pi star, right? And let's assume that we start at state S. Then V star of S is the optimal reward I can get if I start at state S and I follow the optimal policy. The best reward I can hope to get, right? If I follow the optimal policy. And now the interesting fact is that this function, V star of S, the value function, has a very interesting recursive definition, which will then allow us to design a dynamic programming algorithm. It's almost like a shortest path type of recursion. Okay, and let's look at it. So let's assume that pi star is our optimal policy, right? And let's assume that if I start in state S1, pi star will tell me do action A1, then get into state S2, then do action A2, and so on, right? Potentially probabilistic, like S2 might be probabilistic, right? And so then obviously if we expand out by just using the definition of a long-term expected reward, I can observe that the V star of S1, right? So the value that the optimal policy gives me if I start in state S1 will be the expected reward I get from if I'm in state S1 and I do action A1, because the reward can be a little bit probabilistic as we discussed. And then plus the expected value of gamma times the reward I get if I'm in state S2, which is the next state, and I perform action A2, and so on. So the discounted reward, right? And here this expectation here is actually this expectation. The second expectation is over the second state we might get in, right? Because the transition is probabilistic, right? And also over the reward, because the reward function is probabilistic too. Okay, but if you just unroll it out, we can observe that actually if except for this first term, right, except for the very first term here, when the rest looks very much, if I factor gamma out, when the rest looks very much like what we had at the beginning. So then I can just observe that this is the optimal value, the value of the optimal policy if I start in state S1 is the expected immediate reward plus gamma, right, is the expected reward of the first action A1 plus gamma times the value, the expected value over the states S2 reached by performing action A1 from the state S1 of the optimal value V star of S2 of performing the optimal policy from the moment on. Right? If I just write down what the recursive definition of, I just unroll how the value, optimal value for state S1 looks like, and I just observe that when I look at it, the second terms, if I factor gamma out, then I get something that looks very much like what I got. Okay, and then I get this recursive definition. Okay, or another way to say it, and it's basically an equivalent way to say it, it's exactly what I have here. So the optimal value, now let's assume generically, if I start in a state S, the optimal value of any state is the expected reward that I get by performing pi star of S in the state S, plus gamma times the expected value over the states, to be gamma times the expected value over the states S prime that I can reach by performing action pi star of S, what my optimal policy term is to do from state S. So the expected, right, so it would be the expected value over the state S prime I might reach in the next step of the optimal value I get from state S prime, or what I get if I perform optimally from the moment on, right? So that's the recursive definition of the value function, optimal value function. Right? Is this clear to everyone? I just use the form of the long-term expected discounted reward, and I just observe it by just doing a little bit of reasoning. You observe that so for any state S, the optimal value, the value of the optimal policy for that state S is the expected reward, immediate reward that I get by performing what my optimal policy tells me to do in that state, plus gamma times the expected value over all states S prime I might reach by performing pi star of S of the value of the optimal policy from that moment on. Okay? But now why is this interesting? Because this immediately suggests an algorithm for computing these policies, for computing this. So if everything is known, if I know the probability, if I know, for example, the transition probabilities that tell me if I'm in a certain state, I perform a certain action, what is my next state? If I know these transition probabilities and if I know the state space and the action space, I can use this recursive definition to come up with a cool dynamic programming algorithm for computing this. And this is pretty much like a shortest path type of algorithm. So for those of you familiar with Bellman-Ford algorithm for shortest path, it's exactly instantiated here for this problem. Okay, so let me go through it a little bit. So what we're going to do, we're going to initialize. So our goal is we're going to go basically, we're going to come up with closer and closer approximations to V star of S. So our goal is to compute the optimal value for any state S. Right? Right. And so we're going to compute the optimal value, so the value of the optimal policy for any state S. And how we're going to do it, we're going to go through an iterative way to compute that. So I'm going to think about what is the optimal value I can right, how much can I get from a state S if I only do 0 steps, if I do 1 step, if I do 2 steps, and so on. If my robot is only allowed to move 3 times steps, what is the optimal value it can get, starting with state S? Okay, and we're gonna let t go into infinity, and that way we can just converge to V star of S. Okay, so we're gonna use this recursive definition that I had on the previous slide and dynamic programming type of thinking to be able to compute V of S. Okay, and let me go slowly through it. So initially, we're going to initialize this value. So this will be our approximations, right? So initially at time 0, I'm going to initialize V of S to be 0, because if I do nothing, if I'm not allowed to even move once, I'm going to get 0 reward no matter where I am. Okay? And then what I'm going to do, I'm going to go for time steps t equals 1, 2, and so on. Right, for time steps t equals 1, 2, and so on, I'm going to do the following. I'm going to loop through each action and state pair once. So I'm going to go for each action and state pair once. And I'm going to compute these quantities. I'm going to introduce this Q function. So Q of SA So right, I'm going to compute this quantity, which will be Q of SA, which will be basically the reward I get by being in state S and performing action A, plus gamma times, it will be like plus gamma times will be expected value over the states S prime at my reach, if I'm in state S and I perform action A, times V of S prime. Right, or V of S prime was what I had before this loop time t. Okay? And so I wanted to think about it, actually I wrote it here so that you can also guys see it, wanted to think about it, if inductively we think that, so we just entered a loop at time t, right? And let's think that inductively up to time t minus 1, basically, right, so up to t minus 1, let's think that Q of S, that V, right, in the function V, I store the optimal value I can get by doing only t minus 1 time steps. Right, so imagine that, right, so inductively, let's think that when we enter the loop of time t, so right, I said here, we enter a loop at time t, when we enter the loop at time t, we go for all actions and states pairs, and I say, let's assume that inductively, so far, in the function V of S, I store the optimal value I can get from state S if I am only allowed to move t minus 1 time steps. Let's assume that that's the case. Then, if this is the case, then what did I do in my equation over here? What I computed here, what I updated here is exactly, so then Q of S A would be the value I can get by performing action A from state S, and that from that moment on being optimal for t minus 1 time steps. This is what I did here. Right? Because if I'm in action, because I just said Q of SA is just the reward, I get an immediate reward, and then I'm going, there will be the expected, that will be sum over all states S prime that I might reach. The probability that I reach S prime given the state S and action A times the optimal value I could get in t minus 1 time steps if I'm starting in that state S prime. Okay, and then now if I then take maximum, so this is for a state action pair, right? But then if I take maximum over all possible actions I might do in state S, then what do I get? Then I get that at the end of this the loop time t, then in V of S, what do I have? It will be the optimal value I can get after t time steps, right? Because the optimal value you can get after t time steps, well, what you will be doing? You should be doing the action so that if you sum the immediate reward plus the reward, the maximum reward you can get in t minus 1 time steps, that will give you exactly the optimal value you can get in t time steps. Right, so this is exactly the type of dynamic programming algorithm, right? So if you guys know in dynamic programming what we do, we have a problem that we really want to solve, and we define sub-problems, and we show how to use, like, so in this case, the sub-problems would be, what is the optimal value I can get if I start a state S, and I'm allowed to move up to t time steps. And what we showed, and we encode this in the quantity V of S, right? And what I showed is how to compute, given a sub-problem, how can I compute the value of my sub-problem, which is V of S in this case, if I know the value of its corresponding sub-problems. So in other words, if for any state action pair, I know, for example, the optimal value I can get, sorry, if for any state S, I know the optimal value I can get if I'm allowed to only go t minus 1 time steps, then I can use that, and I can use this update over here to then compute, I can use that information and this update over here to then compute what is the optimal value I can get from a state S if I'm allowed to go t time steps. Right? So that's the idea of dynamic programming. We define sub-problems and we show how to use solutions to sub-problems to come up with the solutions to even bigger problems. And here the nested family of problems is the optimal value I can get if I'm allowed to go for t time steps. And when I iterate for t from 1, 2, and so on, I can let it grow arbitrarily large. Yeah, is this clear? So if you guys are familiar with algorithms, it's pretty much just Bellman-Ford algorithm for shortest path. Yes? Say it again.
The policy P we need to update, right?
So here I'm just computing the value function.
We are not computing the optimal policy.
Right, so I'm only computing the value function. And I guess the question is, if we know the value function, can we compute the optimal policy? And the answer is, right, so if we know the value function, and if we know everything else, can you compute the optimal policy? So here I'm only giving an algorithm to compute the v values. Okay, and I claim that if we manage to compute these values, these optimal values, we can, and if we know everything else, the transition probability and the reward function, we can compute the optimal policy too. Do you see how?
When we have the deep, we can query the back pointer each time we take the optimal decision and advance it.
Yeah, so that's only to do it, absolutely. Yeah, so at the end of the day, when you are done finishing, you can just go right, exactly. So one solution is what Sweta is saying. You can use, okay, so if you have algorithms, that will be the right answer. So you can just use, right, so for example, okay, in algorithms terms, here I computed, I have sub-problems, and I computed the value of the sub-problems, and to find the optimal policy, I can do some smart backtracking, as what I'm saying. That's kind of the typical algorithms answer. But even without knowing DP so much, you can also see that if I know I don't have a marker today, unfortunately, but basically, actually maybe I can write on the board. But let's assume that, okay, so let's assume that even you don't even want to go into this inside this DP, for example, inside this dynamic programming. But let's assume that somebody gives you V star of S, the optimal value for any state S, right? And I know the transition probabilities and I know the rewards. Now, how do I compute the optimal policy? Well, so what do we know? We know that given a state S, pi star of S, is there something I can write with? I should be. Okay, I'm just going to write on this side. Right, so the simplest answer is what Sveta said, but if you don't want to go inside dynamic programming, then a different answer will be, right, so what I know, what is pi star of S? So it's the best, right. I think it will be basically, so I need to take the best action, right, from that moment on. And so to be R max over A of the reward. So I have, if I'm in a certain state S, I have a certain possible actions I might take, right? And I'm going to think about which one of them is the best one. It will be, I'm thinking about the best possible action. So I have some immediate reward, right? Plus, this is the immediate reward. Plus, when I'm going to discount, right, I know the transition probabilities. I know where I might go. So it's sum over. And it will be the probability of landing in a certain state, S prime given S, and by doing action A, times V star of S prime. Right? So I know. So basically, I know that given if I'm in a certain, right, so if I'm a certain state S T, that should be S. If I'm a certain state S, and I perform a certain action, I get, this is the immediate reward that I can get. Right? And for the optimal policy, I know that I must be also optimal from the moment on. Right, so this is what I get for the if I follow the optimal policy from the moment on. But I know what I get if I follow the optimal policy from the moment on, because I know V star, I know the value function, and then basically when I want to think about what optimal action should I be doing in state S, well, I should be doing the action gives me the best reward.
Store the value functions in an array for all the states.
Say it again.
We need to store the value functions in an array.
We need to store what?
Value functions.
Value functions. We need to store them. Yeah. Yeah. Okay, so is this a clear answer? So I'm just saying you can also, if you know the value function, you can immediately end the reward function. If, you can immediately compute the optimal, what you should be doing, what the optimal policy is telling us to do in every single state, but just expanding out what is the value you get for that state, right? And that's one solution, but another solution actually, as Sweta said, if you know dynamic programming, you just backtrack. You just get, it's exactly, okay, you just take the action that maximizes this. That's pretty much it, right? I guess this is pretty much what I wrote there too. Good. Great. So that's pretty much. So let's actually go quickly through this example too, because we do have the time. So if you go through this example, so let's see. Just let's run this algorithm in this example, right? Let's have it in this example. I need to go 3 rounds. So what is the v value after in time 0? Well, I can tell you that one. So in time 0, the v value is 0 for all states, because this is what we initialize. How about after 1 time step? What is the v value? How do they look like?
The max you can reach is 81.
After 1 time step? So think about this algorithm. I want to run this algorithm. After 1 time step, I don't think I can go to 81 after 1 time step. Because I need to follow this algorithm, right? So I'm thinking, so at t equals 0, everything is to be 0, 0, 0, 0. When t equals 1, I'm going to, what is the t equal 1, I'm going to encode what is the optimal value I can get if I'm allowed to go one time step. So then the best I can get is only 100 and 0, right? So what will happen is this guy will going to get value 100, this guy will going to get value 100, this will remain 0, this will remain 0, because if you guys go one time step, you can only get 0. So then basically, it's exactly what I wrote here on my slides. After one time step, the top row is going to be, so I'm going to have value here 100, because if I'm allowed to go a one time step optimal, I'm going to get value 100, because I reach the goal, I get this. It will be remain 0, because now in one time step, I can only get 0 here, no matter how optimal I am. So this will be 0, 100, 0, and this will be 100. Here will be still 0, and this here will be still 0. How about the next time step? So now, after t equals 2, what v of t we're going to encode is the optimal value I can get from that state if I'm allowed to behave optimally for 2 time steps. How are the values looking like? Yeah, so that to be, as you said, because here I already have, here I had 100, right? So now if I'm allowed to behave optimally for, so for example, I start here, I'm allowed to behave optimally to 2 time steps will be 0.9 times 100, right? So you are right, it will be 90, 100, 0. Here will be what? 100, here will be 90, and here will be still 0, right? Okay, and how about the next time step? I'm giving it away, it's obvious. Then I can also, I'm going to get 81 here, and everything else will stay the same. Right? And after, if we go for t equals 4, nothing changes, right? Because there's nothing more I can improve. Okay, so that's an example how you can run this Bellman-Ford-like algorithm to compute the value function if we know everything about the description of the game. We know the transition probability, we know the reward function, we know the state and actions, everything. Okay, cool. Great. Okay, and so, right, and because gamma to the t goes to 0, as t goes large, right, I mean, so in this example, everything stopped, nothing updated after t equals 3 week, and basically the reached steady state for these v-value functions, because it's a particularly simple example. That might not be true in general, right, because it might have a much larger action space, much more intricate reward and transition probabilities. But it turns out because gamma to the t goes to 0 and gamma, because gamma is to 0 and 1, will eventually reach a moment where nothing will change much. And so then we can just stop. So once we kind of, once there isn't a significant change in the v-value from one iteration to the others, then we can just stop. Okay? And I guess formally, this is my second point that I have on my slide here. So formally what we can show actually, and this is what was shown, that if I have 2 subsequent iterations, say t and t plus 1, and the maximum change in the v-value was at most epsilon, then we know exactly by how much, how close we are to the optimal policy. Yeah? In particular, while the current policy, the value of the current policy differs from the optimal policy by not too much. Okay, you can bound that. So when people have proven that, right? So we can safely stop once there isn't much change in the value function. Okay, that's one point. And another point is, so far actually, if I go back to my dynamic programming algorithm, by the way, dynamic programming is one of my favorite algorithmic techniques. So if you're not a computer scientist and you don't know it, you should definitely learn it. I have nice lecture notes about it in my algorithms course, so if you're curious. Good. So, right, so if we go back here, so when we do this dynamic programming type of strategy, we in a very principled way, we cycle through each state action pair, right? In a very, very principled way, we cycle through each state action pair. So in each round, we went through each of them once. Now it turns out, and that's kind of cool, that actually we don't even have to be so methodical. So it turns out that the value iteration algorithm works. We can prove that if we converge, even if the agents move randomly in the environment somehow. So even if you don't have to be so methodical, right? For example, here, right? So maybe would we do it here? Maybe here we say we did it something, right? You don't have to go so methodically. You can just go randomly, but as long as you visit each state action pair infinitely often, you are done. You are good. Okay, and this was a theorem proven by Bert Tsekas in '89. Okay, and that's nice because the implication is that this kind of leads to an online learning algorithm as the agent just walks around, right? I mean, so yeah. This looks more like learning, right? You know, you do some actions, explore your state space, and so on. Okay, so any questions about this so far? Is this all clear? So the reward, I'm assuming, is non-negative, right? It's an excellent point, because otherwise my DP might... so actually this still works, you know, if you guys remember, Bellman-Ford algorithm still works if we have no negative cycles. But it's much simpler. For simplicity, let's assume that we have no negative rewards. That's an excellent point, actually. If the reward was allowed to be negative, and even worse, if I had negative cycles somehow in my graph, then this would break, right? I mean, as I described the algorithm, I'll almost give you a proof of why this algorithm is correct, right? Because I said inductively, I'm going to argue that V of time t, V of t will be the optimal value I can get. Like the time t, V of s will be the optimal value I can get from state s if I'm optimal for t time steps on, and then move only t time steps on. And I argue that inductively, as I described the equation. That was only true if the reward was negative, as you pointed out. Yeah, excellent point. Yeah, so here we only want to reward the agent. We don't want to punish the agent. Okay, cool. So that's the value iteration, where you can actually basically compute the value function for every single state, which is the value of the optimal. So we basically, this is an iterative algorithm for computing V star of S, which is the optimal value I can get from that state S, optimal discounting value I can get from that state S if I'm behaving optimally from that state S from the moment on, right? And we argue that this algorithm gives us a very good approximation of this star value function, but to run this algorithm, I really need to know the reward function and the transition probabilities. Okay, and your name was? Yeah? Yeah? Kirsty, right? As Kirsty was asking, okay, what more interesting case is when you actually don't know these quantities. When I don't know the reward function or the transition probabilities, what can I say then? Right, so I guess more specifically on that, not necessarily the transition probability. Now, of course, in order to hope to do anything, if I perform a state action, if I do an action, I should be able to at least observe some immediate reward. Either I know it or somebody tells me right then, right? Because otherwise there is no hope, right? If I get no information about the quality of my actions, right? So let's think about the case where we don't know the transition probabilities. And the reward is either unknown, but we observe it as we perform the action, or it's known. Okay, and the cool thing is that it turns out that we can use similar ideas to come up with an algorithm. And it's pretty much will be kind of an asynchronous version of this dynamic programming that we had here. Okay, and so what is the key idea? So right now, so here this is the value iteration algorithm for learning the V star function. Now when we define this V star function, we also had this Q function, right? And to define this function, right? To define this function here, we had the value iteration for computing the V star function, and we have this V function. To define it, we needed to know the rewards, right? Because if you look here at this update here, I definitely had to know the reward to update it, right? But it turns out that instead of I can just somehow directly design an algorithm that just learn the Q function. So I'm not going to try to attempt to learn the V functions. Instead, I'm going to learn the Q functions. And somehow that's why this is called Q learning, and that would allow me to deal with the case when I don't need to know the rewards up front. I don't need to know the transition probability up front. Okay, and here is the idea. So, right, we had these two quantities. The V star of S was the expected discount reward following the optimal policy from time 0 onward. Good, and then Q of SA, if you guys, this is what I used earlier, right, was let me define it to be for the optimal policy, will be the expected discount reward of first doing action A and then following the optimal policy from that step onward, right? So if I do an action A from a certain state S, I'm going to get probabilistically potential to a state S prime, but then I'm going to follow optimally, I'll be optimal from the moment on, right? So then the notion, the Q of SA is basically, this is a recursive definition, right? This is actually the definition of Q of SA, is this equality that I have over here, right? So Q of SA by definition is just the expected discount reward of first doing action A and then following the optimal policy from that next step onward, right? And given this definition, this is how it looks like. Okay, now the point is that somehow if we manage to learn a good approximation of this function, of this pairwise function Q of SA, right, then we know how to act, right? And we know how to act without ever knowing these transition probabilities. Right, so imagine that you have a procedure to somehow learn this Q function. Then I know how to act because all I have to do, given a state S, I just need to pick the action A that maximizes Q of SA. Right? That's by definition. So somehow if magically if I'm managing to learn this Q function, then I'm done because I know how to act. And I don't need to know the reward or anything or the transition probability. Okay, so that's the basic idea here. And it turns out that yes, we can learn actually the Q value. So we can directly learn the Q value by just operating in the environment without ever having to know the transition probabilities. And it's pretty much like the dynamic programming algorithm that we use to compute the V function, the value function. And essentially it all boils down to, again, the fact that basically, right, so it will be boiling down to that we can again write a recursive definition. So how did we handle the V function? We wrote a nice recursive definition for V function, and then we came up with a dynamic programming algorithm for doing so, a principled way, efficient way to compute the V function based on the recursive definition, right? Turns out we can do the same thing for the Q function. Okay, and that's nice because then we don't need to know the transition probability. Okay, so, oh yeah, and here I have some, let's see, so here I have an example, right, so the same example, these are the V star values, I think we already talked about them, and you can also write down what is the Q of SA, right, so for example, let me just go through one of them quickly, just to make sure that we are on the same page. So for example, the Q of SA, so if I'm, for example, in this state, right, this is my state, up, bottom right, that's my state, and if I'm told go to the left, right, then what is the Q value here? Well, I have to follow that action. I'm just talking about it in principle, right? I mean, so I'm just giving an example of what the Q value means, right? I will have to follow that action, so I get reward of 0. But from that moment on, I'm optimal, right? So if I follow this action, I get reward of 0. But from that moment on, I'll be optimal. So I'm going to get 0.9. I'm going to discount to be 0.9 times 90 because this is the V function for this state. So I claim that, for example, if I'm in this state and I have to go the action go to the left, then the Q of SA, so Q of being in this state and doing left action will be 81. Because I must perform the action, I get a certain reward, and then I'm optimal from that moment on. Okay, this is just to instantiate what the Q function means. Okay, but now the cool fact is that this Q function, we can write a recursive definition for it. Okay, that's really what saves the day. And then we can come up with an algorithm for learning it without having to know the rewards. Okay, so, right, so by definition, V star of S is the maximum, the optimal value of a state S is just the maximum over all actions A prime of Q of S and A prime. Right, that's just by definition of the Q and V star functions. Okay, and so basically using this, then we can just write down and the definition of the Q function, we can just observe that the Q of a state ST and the action AT is the reward you can get from that state by following that action plus gamma maximum over all states A prime of Q of, this should be, of ST plus 1 and A prime. Right, or ST plus 1 is a new state that I'm getting in. It's just okay for simplicity, I guess I assume there. So right now I'm showing the algorithm for learning the Q function if we assume the transitions are deterministic. It just simplifies things. Right? If the transitions are deterministic, if I'm in state ST and I do an action AT, I deterministically get into the state ST plus 1. Right? And I'm saying we can immediately write a recursion for the Q function, which just means the Q function for the pair ST AT, if I'm in the state ST and I do action AT, is just the reward I get by doing so, plus gamma times, by definition, will be maximum over all states A prime of Q of ST plus 1 and A prime. Okay, but that's a recursive definition for the Q function. And so this immediately suggests basically an algorithm, an iterative algorithm for computing the Q function, which is very much like the dynamic programming algorithm we had for the V function. Okay, so in other words, if Q hat is our current approximation, right, and if we are in the state S and we perform a certain action A, we're going to get some reward, right, because we get feedback, immediate feedback, a little bit of immediate reward, right, and then we update our Q hat value, right, by adding by adding to this reward gamma times basically the maximum overall state S prime of Q hat of S prime and A prime. Yeah, so basically the recursive definition of the Q function immediately suggests a method to try to update our Q values as the robot goes into the world. Right? So the robot or our agent will do just it's in a state to do some action. I can use that information and the immediate robot I get to update my Q values. It's very natural. It follows very much the idea of the way we did for the value function. Now it's not as right. It's not necessarily. Yeah. Okay. Good. So that's the algorithm. Good. So that's basically this immediately suggests a learning algorithm. Now you don't even have to go methodically through like all states and actions pair. We just let the agent act into the world. I only have a minute actually left. So right. So when basically this recursive definition over here immediately this recursive definition over here immediately suggests a learning rule. We can just write an algorithm that implements the learning rule. And you can also try to see what the learning rule does on now a specific example. You can go through it offline. Now, the interesting fact is that if the rewards are non-negative, then this Q hat estimates are only going to get closer and closer to the true Q functions, to the true Q values. And moreover, we can also prove that if we visit each state action pair infinitely often, then this really converges to the right Q values. Okay? And once you have the right Q values, then that's great, right? Because you know how to act, right? And to compute, and again, the cool fact is that to compute this, to implement this algorithm for learning the Q values, you do not need to know the probabilistic function, transition function. You only need to just act in your environment, and to get guarantees, right? So you can just implement this algorithm, right? Where when you do a state, you're in a state to do an action, you can update your Q hat estimate for the Q function, right? And you are guaranteed that if you visit every state action pair infinitely often, you're gonna get great. This will converge to the truth, okay? And I have a proof here, and you can read it offline. It's actually not very simple. It's not very complicated. You just it's here. It's just a small trick. Good. Okay, I'm running out of time, so let me just. Obviously, in the deterministic case, in the non-deterministic case, you had to add some randomization. And things go through smoothly. Okay, but just to summarize, right? So today we've been talking about reinforcement learning, which is a very different type of learning paradigm than we've talked about so far. It has the cool aspect that the main impact of our action is not immediate. It's like we only observe that main impact later on, right? Maybe after, in the backgammon case, after we play the game, we observe did we win or lose, right? But somehow we do get small rewards as we go along, but the real impact comes later on. Okay, and the idea to deal with such so we have delayed reward, and the idea to deal with such scenarios is to learn these evaluation functions, either the V function or the Q function, that somehow for any state S, or for example in the V function for any state S, it tells us what is the best value I can get if I'm optimal from that state S from that moment on. Okay, and then by using these ideas and cool dynamic programming algorithms, we manage to operate well in these environments. Great.